finally, the situation where we have 4 defectives, which is that guy right there, there's only one of those. There's only one way to have them all defective. And plus, we've run out of possibilities. These are all the possibilities that we have. And all of these probabilities, if we took these individual ones and added them together, guess what? We'd get 100%. Because in this diagram, we've accounted for every situation for all 4 of those light bulbs. So this one, well, we'll have 4 Ds, so that's 0.2 times 0.2 times 0.2 times 0.2. But just for consistency, that also means that I'm multiplying by 0.8 0 times. So remember, anything to the 0 is 1, so really this is just 1 times 0.2 to the 4. Now on the next page, I've actually gone through and I've made these calculations. So I've actually done this in my calculator, and these are the probabilities I got. 0.4, 0.4, 0.15, 0.03, 0.0016, and I've drawn the probability distribution. So here are the number of defective light bulbs, and here are the likelihood of having that many defective light bulbs. So we see that this is a right skewed, and in fact it does appear to be the case that the likelihood of having more and more defective becomes less and less. Okay, well, let's try to make the distinction that we're seeing here is if we denote the thing that we're keeping track of. So let x equal the number of defective. Well, we consider the situation to be a success. Now, don't take this literally, but in this experiment, a success is if a defective is found. A failure is the opposite, so not defective. And there are really 2 states here. Every outcome is either a success or a failure. So this has 0 successes, 1 success, 2 successes, 3 successes, 4 successes. Success in this context just means that what we're keeping track of has happened. And so really what we have here is, let's call P equals the probability of success. Well, that means that 1 minus P is the probability of failure, of not success. So in this context, 0.2 is the probability of success, 0.8 is the probability of a failure, that's not defective. Okay, well, look at what's happening here. We have a number times the probability of a success raised to the 0 power. Well, the powers here represent the number of successes. 0 successes, 0 power. 1 success, 1 power. So we'll call S equals the number of successes. So that means we have an S up here. Well, then we have 1 minus P, so now we have the remaining failures. Well, how many failures do we have? Since we're talking about 4 in a batch of 4, well, let's call the number of possibilities, or the number of objects, let's call that n. More generally, I'll refer to that as the total number of trials. So we have 4 trials, and in those 4 trials we could have any number of successes between 0 and 4. So that means that this is really just 4 minus that, because these are always adding up to 4. So generically we would say n minus s. Well, this number is not very obvious where this is coming from, but as a matter of fact, if you do n combination the number of successes, that's going to give us the corresponding coefficients here. So for instance, I'm going to come over here to Excel and I'm going to type in equals combination 4 possibilities, 0 successes, and look at that, I get 1. Now if I take 4, choose 1, I get 4, and that happens to match my coefficient here. If I do 4 combination 2, I get 6, and that matches this coefficient here. These are called binomial coefficients, and most of the time, instead of writing it this way, we would write it and choose s. So these are identical notations. So I'm going to replace this number sign here with n combination s. That's the number of ways you could get 0, 1, 2, 3, or 4 successes. Probability of a success raised to the power of the number of successes. 1 minus p, so the probability of a failure, raised to the power of the number of failures. So really this is a more complicated looking form of what we actually did here, but it's a nice shortcut. So this is the probability that x equals